mind, you should memorize, you should know what the graphs of these basic functions look like, the graphs for these easy power functions. So first, if I have a power function, y equal x to the n, where n here is an even integer, then it looks something like this. If n is 2, y equal x squared, it's a parabola. It's what we've just studied. Looks like the graph of a parabola. If n is larger than that, let's say like 8 or parabolic like, but it'll be much sort of flatter here, and then it'll go up much faster as you go out past 1. So between plus and minus 1, it'll be relatively flatter here, and then after 1, it'll be much steeper. Okay, next. If n is an odd integer, not equal, then it looks sigmoidal, just like what we did in the last section. We had a cubic. And as n keeps getting larger, it'll look more box-like, more squarish. If n is equal to 1, it's just the graph of y equals x. Is just the line having slope of 45 degrees going through the origin. Next, if n is 0, so that's the graph sketch of y equal 1, it'll be just a horizontal line. If I try to sketch the graph of y equaling 1 over x to an even power, then it looks something like this. So it will peter out as we go to plus or minus infinity, and it'll blow up at 0. If I try to sketch the graph of 1 over x to the n, where n is odd, then again, it'll look like this. So notice that this is for the graph of 1 over x to the n, where n is even. If n is odd, it'll be symmetric about the origin. It will still blow up at the origin and peter out at infinity. And it'll look like, at least in the first quadrant, something very similar to what we graphed above, but you'll reflect it about the origin so that it's symmetric about the origin. So one looks like this, the other looks like that. Next, suppose we look at the nth root of x. And so if n is even, then it looks something like this. It looks like a square root. Or it looks like half of this turned over on the side. So you just take this part, turn it to the turn it over, basically reflect about the line y equal x. Then you have this graph. Next, suppose I have the nth root. I want to sketch the graph of y equal the nth root of x, where of course n is not equal to 1. You can't take the 1th root. And the index is odd. So I take the odd root. Well, then, and so what you notice is this is just a reflection about the line y equal x of y equaling x to the n, where n was odd. Okay, we could do some more of these where it's y equal x to the p over q, but those become more difficult. So I'll just leave it as you should know these powers power functions. In addition to that, the absolute value. So the absolute value just looks like this line in the first quadrant and this other line in the second quadrant. So it looks like y equal x in the first quadrant and y equal negative x in the second quadrant. Just recall that a polynomial looks something like this. The number of extrema is always less than the degree of the polynomial. If the leading order coefficient is positive, it goes up into the first quadrant. If the leading order coefficient of the polynomial is negative, it goes down into the fourth quadrant. If the degree is even, they go into adjacent quadrants. And if it's odd, they go into opposite quadrants, the tails I'm talking about. So there are 4 transformations that we can apply to the simple functions, and we'll get more complicated functions. So most of the functions, not every one that we'll be dealing with, but most of them that we'll be dealing with are just transformations of simpler. So the first that we'll be talking about is translations. A translation is just moving a rigid movement of a graph of a function, right, left, or up, down. And you can do any combinations where you keep going up, down, right, left of the sketch of the graph. A reflection. A reflection is, well, you take the sketch of some function and you reflect it about a line or about a point. Talking about reflections about an axis, the x-axis, the y-axis. Scaling. So in scaling, you're either compressing or stretching by one of the axes. So you can think of this as following. If you get some, not Play-Doh, some, I think silly putty. I think that's what it's called, not Play-Doh. Play-Doh's the other one. Some silly putty. If you get some silly putty, then what I did when I got silly putty was I didn't really play with, well, I did play with a lot, but the first thing I would do is I would find a newspaper with usually a color picture of someone's face or something, and I would press the silly putty onto the picture and carefully peel it off so you had a nice representation of one direction compressed in the other direction. And that's what scaling is doing, is you're stretching in one direction or you're compressing in that same direction. Or, so in the x-axis or the y-axis, you're going to take your graph, you're going to compress it, or you're going to stretch it in the x-axis. You're going to take the graph, you're going to either stretch it or compress it in the y-axis. Next, rotation. We actually won't be doing rotations in this class. If you took the equivalent class that involves trigonometry, which is called pre-calculus, Math 259, pre-calculus with trigonometry, Math 260, pre-calculus, or, well, in Math 262, which is actually a calculus class, they discuss rotations. We won't actually do that in this class, other than I may just say quickly and briefly, you rotate this about an axis or something, or about the origin or something. But we won't discuss it in any meaningful detail at all. So let me discuss each of these 3. Translations, reflections, and scaling for a particular function. Let's say y equal f of x. let me assume that h is greater than 0, k is greater than 0, and a is greater than 1, so that I don't need to state that further in the things I'm going to be doing. So suppose I have the following transformations. I will then tell you what the results will be. So first, let me describe translations. So suppose you replace y by y minus k. Then you'll translate k units in the positive y direction, positive because it's negative y direction, which means you're going to be going up. So you'll move your graph k units upwards. Next, suppose you replace y by y plus k. Then you will translate k units in the negative y direction. You'll go k units down. Suppose you replace x by x minus h. Then you will translate h units in the positive x direction, h units to the right. Suppose you replace x by x plus h. Then I'll be going h units in the negative x direction. I'll translate h units to the left. So in general, think of the following. Math is always backwards. So if you subtract, you go in the positive direction. If you add, you go in the negative direction. Let's do reflections. So I've written these so that all of them will be backwards. So they'll Albert's thing. So reflections. So suppose you replace x by negative x. Then you reflect about the y-axis. Suppose you replace y by negative y. Then you reflect about the x-axis. So now let's talk about scaling and compressing. Suppose I replace x by x over a. Again, I'm assuming a here is greater than 1. Suppose I replace x by x over a. Then I will draw the sketch of my function where I have replaced x-axis by multiplying it by a. So I will stretch the x-axis by a factor of a. I'll multiply by a in the x direction. So if I have the transformation x, where I replace x by x over a, I will stretch the x-axis by a factor of a. Now suppose I have the transformation x going to ax. So I'll replace x by ax. Then I will take the x-axis and divide by a. So rather than multiply by a, I'll divide by a. So I'll compress the x-axis by a factor of a. So if this was 2a, then I'll compress the x-axis by a factor of 2. I'll make it half the size. Suppose the transformation is I replace y by y over a. Then I'll stretch the y-axis by a factor of a. If I have going to ay, then I'll compress the y-axis by a factor of a. So we've actually sort of used this. So let me explain how we did this before, or how you did this before. So suppose you start out with the graph of y equal x. Well, we know that. I did 5 minutes ago, and you obviously knew it from way back. So this is just the graph of a line passing through the origin, having a slope of 45 degrees. So if you go 1 in the x direction, positive x direction, you go up 1 in the positive y direction. However many units you go in the x direction, you go that same number of units up in the y direction to get to another point on the line. And so that's the graph of y equal x. Now, suppose I look at the graph of y over m equals x. Then, and suppose m here is greater than 1. So it means I'll be stretching my y-axis by a factor of m. So this 1 multiplied by m, it'll be stretched m units. So now if you go 1 in the positive x direction, you be going up m units. And if you look at that, well, that's a slope. Now, if I had if I replaced it by a negative y, then I would reflect this about the x-axis. So I reflect this about the x-axis. So instead of going up m units, I'd be going down. Gives me the idea of a negative slope. And so this concept of slope, y equal mx, is just really the idea of reflection and scales. Now, suppose that I take the graph the curve h units in x and k units in y. Then y is replaced by y minus k, x is minus h. This is what we called the point slope form for the equation of line. And so line that we gave you was really just starting out with y equal x, doing translations. And so even though we didn't really discuss it back when we looked at those 2 or 3 weeks ago, the last time we met, it really is something of that form. Okay, so let me do problem on page 339, problem number 16. I probably need some more room. Yes, I will. Okay, so let me give myself some more room here. Page 339. The graph of each function is a translation of the graph of y equal x squared. Graph each function. Okay, so let's do that. So first thing to do is to replace h of x by y. So I have y equal x minus 3 quantity squared minus 1. Now let's add 1 to both sides of my equation. So I have y plus 1 equals x minus 3 quantity squared. So now this just looks like a translation of y equals x squared using the following translation. So you're going to translate this to the right. So I'll go in the positive, because this is a negative number, a positive x direction, 3 units. Well, 3 units in the positive, well, positive x direction is right. So I'll go 3 units to the right. And So 3 units to the right. And I'm adding 1, so I'll go 1 unit in the negative y direction, so 1 unit down. So let's sketch the graph of this. Okay, so first off, let me sketch the graph of y equal x squared, because I'm doing a translation of this. So y equal x squared looks something like a little bit steeper. Okay. Good enough. It's not quite symmetric, but okay, not too bad. Okay, so this is the graph of y equal x squared. Okay, so that's why I told you that you should memorize those basic power functions that I gave you. So you should know each of those, what the graph of each of those looks like, because you'll be asked to sketch one of those basic graphs and then do some sort of translation, scaling, or reflection to get something more complicated. So now I'm going to move 3 units to the right and 1 unit down. So, okay, stop that. So I'll go 3 units to the right and 1 unit down. Okay, so this vertex will be here, and I'll translate. So if you recall, we said that for the standard form, all of a sudden that once you translated, that once it was in the standard form, that the vertex was found by what each of these were, which turns out to be really a translation of the graph of y equal x squared. And then I said something to the fact that, well, it depended here if a was greater than 0 or less than 0, if it went up or down, meaning, oh, it's just a reflection about the x-axis or not. And if a were, the absolute value of a were greater than 1, then the for that is because I was stretching the y-axis by a factor of a. And so all of those properties I gave you involving, like 20 minutes ago or half hour ago, involving how to sketch the graph of a quadratic, was really just knowing the graph of y equal x squared and applying transformations to it. And that's really all I did. So this is the graph of y equaling x minus 3 squared minus 1. Okay, so let's do. So this is already in a nice form, so we can tell what the transformation is. So this is just a translation of y equaling x cubed. In this case, well, we'll be going 5 units in the positive x direction. So I'll be going right by 5 units. And I'll be doing 7 units in the positive y direction units up. So let's try to sketch the graph of this. As best I can. So originally we have the graph of y equal x cubed, which looks something like this. Now I'm going to go 5 units in the x direction and 7 units in the y direction. So I'm going to take this 5 units. So 1, 2, 5. Okay, so let's do 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 5 units in the x, so it should be, well, that's not too bad. That's pretty good. So this is the graph of, oops, except that I did it wrong. I wonder if I can, oh, I can. So actually that's even better. So I started out, well, good enough. It didn't look the same. Let's see if I can actually let's just get rid of this. Delete. So I'll start with this. Okay. See if I can grab just one. Oh, I grabbed both of them, wouldn't you know it? If I can't do it, then I can't. Okay. So just forget that I did that. Okay, so let's say it looks something like this. Okay. Good enough. Okay, so it looks close enough to the original graph. So what I'm going to do, I go 5 in the x and then 7 in the y. There. And so that's what the graph looks like. It looks something like this. So I started out, here, let's not make it go all the way up. So I started out, and maybe I'll even have it go down further because I started out with the graph of the of this original this original function. That really looks horrible. Yeah, it still looks horrible, but okay, so this is the graph of y minus 7 equals x minus 5 cubed. So I started out with this function. And I just translated it. Yeah, that's not so bad. That looks a little bit better now. So I started out with this red function originally, and I just moved it 5 units in the positive x direction, and then 7 units in the y direction. 1, 2, 3, 4, 5, 7. There. So I basically took what this graph looks like here and moved it. I'm just showing the origin so that you can see it, quote unquote, move 5 units in the x direction and 7 units in the y direction. Okay, let's do this. Cube root. The graph of each function is a translation of the graph of y equal x cubed, y equal x squared, y equal x cubed. It's not a translation, it's a reflection. Graph the, it's not a translation. This must have said a reflection because it's not a translation. This is a reflection. The graph of each function is a reflection of the graph of y equal x squared, y equal x cubed, y equals the absolute value of x, y equals square root of x, or y equal the cube root of x. Graph each function. So I have here h of x is equal to negative x cubed. So let's replace h of x by y. Let's multiply both sides of my equation by negative 1. So negative y equals x cubed. So now it's in the form where I can replace y by something, by negative y. And so this is a reflection of y equal x cubed. And this is about the x-axis. Okay. Oh, I wonder if I'll do it here. Maybe let's do that. So let me just partition my page into 2 pieces here. So I have some room. So I'll start with the graph of y equal x cubed. I don't draw y equal x cubed the best. That's why I was having trouble in the last one. So let's draw the graph of y equal x cubed. There, that's not so bad. This is not so bad. So this is the graph of y equal x cubed. And now what I want to do is I want to reflect it about the x-axis. And so let's just take this and reflect it about the x-axis. So now it's going to look something like, not so bad. Okay, that's not horribly bad. So this is a graph of y equals minus x cubed. And so this in black is a graph of y equal minus x cubed. Okay, let me do, this is again not a, this is a scaling. Okay. The graph of each function is a scaling of the graph of y equal x squared, y equal x cubed, or y equal absolute value of x. Graph each function. Okay. So let's replace f of x by y. So this is y is equal to absolute value of x over 3. Okay, so actually let's write it this way. So y is equal to, let's multiply by 3. So 3y is equal to absolute value of x. Okay, so I'm going to divide. So I'm going to replace y by 3y, which means I'm going to be taking the y-axis and scaling it down by a factor of 3. So I'm going to take every number along the y-axis and divide by 3. So I'm going to compress. Again, I'll divide this page up so I can draw it. So I'll compress the y-axis by a factor of 3. For the graph of y equal absolute value of x. So let's take the graph of y equal absolute value of x. So I'll start out with absolute value of x. It's not very symmetric, but let's see if I can. Okay, so let's get rid of that. See if I can make it a little bit more. That's a little bit more symmetric. Okay, so now what I'm going to do here is I'm going to compress the x-axis by a factor of 3. Okay. So I'm going to be squashing this. So this guy here will be being squashed down by a factor of 3. So this will flatten out. So instead of being at a angle of 45 degrees, it'll be 1/3 of that, will be an angle of 15 degrees. It'll come down by a factor of 3. Let's see if I can draw that. Oops, wrong color. So let's try that by a factor of 3. By a factor of 3. Okay, so this is the graph of y equaling absolute value of x over 3. Oh, of course, this was y equal absolute value of x. So this in black is now the graph of f of x equaling 1/3 x. Okay, let me do problem 73. We'll need another page for this guy because this will be involving a few things. Okay, so graph each function using a combination of transformations applied to the graph of a basic function. Okay. H of x equals 2 rad x minus 2 plus 1. So first, let's replace h by y. So y 2 rad x minus 2 plus 1. Subtract 1 from both sides, so y minus 1 equals 2 rad x minus 2. So in this case, let's replace y by y minus 1 and x by x minus 2. So if I do that, this is a translation of y equaling 2 rad x by the following. Well, let's see. We're going to be subtracting 2 from x. So I'm going to be going 2 in the positive x direction. So I'm going to be going 2 units to the right. I'm going to be subtracting 1 from y, and so I'll be going 1 unit in the positive y direction. So I'll be going 1 unit up. Okay, now let's divide both sides of my equation by 2. So this is just y over 2 equals rad x. And so this is a stretching. I'll stretch the y-axis by a factor of 2. So I'll be doubling the y-axis for the graph of y equaling rad x. Now, when I do a combination of translations, reflections, scaling, rotations, I go in the opposite direction of the that I've done. So I start with this function. I do this transformation on it. I then do that next transformation on it until I get to the original function. And so let's do this. Let's say we start here. Okay. Let's do 1. Okay, so first I'm going to start with the graph of y equaling the square root of x. So maybe I'll start with red, square root. So this is the graph of y equaling the square root of x. So I want to stretch the y-axis here by a factor of 2. So that means that this is going to be stretched upwards. So this will be doubled in size. So wherever I'm here, I'll double it. So this will go up here. Or that's 1, 2, so this guy would go here. Okay, so let's do green. So now it should.
Hello,
That
excuse me.
is
May
not
I ask
good.
something?
Let's not try to do it that much.
Excuse me.
Okay, that looks a little bit better.
Did you hear me?
Yeah, that looks better. So this is the graph of y over 2
Hello?
equals rad x. Raised hand. Okay.
Hello? Could you
Yes.
hear me?
Yes, I can, just barely.
Sorry, I have a question. In this kind of the work, I want to know which point you change it. If it's exactly which point it's 2 up.
Oh, okay. So I'm just so it's every point. So let's say we're at, the graph is here at this point, and this distance. I then double that distance. So this distance here will be twice that distance.
So we can
So
choose any point.
no, no, you choose every point. So this is doubled in. This guy here is doubled in size. This guy here doubled in size. Every point is doubled in size.
Top of the line. It's on the line. Every point on the line, we can add it to.
Yes, every point on the curve.
Okay.
So the x kept the same. So what you're doing is you're taking, say, the point xy, and you're graphing x twice the size. So you've taken any point, say some point on the graph was 4, 2. Well, let's do 9, 3 was a point on the graph. Then this was, let's do it in color, in right colors. So suppose the point 9, 3 was a point on the red graph. Then 9, 6 will be on the green graph because you double the y.
Yeah, I understand it. Thank you so much.
And it's for every point on the graph. So of course 0, 0 just remains 0, 0.
Oh, okay.
0 because doubling 0 doesn't do anything. So that's why it starts at the same point here. Okay?
Thank you so much. Thank you.
Sure. Okay. Next, what we're going to be doing here, well, it's green, good, is we're going to do a translation. I'm going to go 2 to the right and 1 up. So I'm going to take this graph here, and I'm going to move it 2 units this way and 1 unit up. Okay, so let's see if I can do this. So basically what I've done, let's see, I started out, and that doesn't look very good. Oops. I started out, let's see. Oh, that doesn't look so bad now. I started out with this curve. So I started out with this sort of green curve.
Yeah, now is better understanding. Thank you so much.
And I moved it and 1 unit up. And now, voila, this is, of course, let me get rid of it because it's sort of interfering with everything else. This is now the graph of the function that I want. Okay, so this is the graph of y equaling at x minus 2 plus 1. Okay, so that's what it looks like. So I'm actually taking that green thing and moving it. Oh, and actually I could have thought of, let's see, this red guy. What I would have done, of course I'm going to have to undo it, is I actually double this in size. Voila. so it looks like this other guy. So I just sort of took the graph of it and I just doubled it and I stretched it by a factor of 2. Okay. Oh, and let's undo that because now it's undo the resize. There. So that's all I really did is I just stretched it. Okay. So really that's it for this section.